Hi there. The purpose of this video is to take a look at rational functions and in particular learning how to sketch the graph of a rational function and how to determine its equation given its graph. Now if you think back to earlier lessons, you would have dealt with rational expressions. So just in terms of an example of a function, f of x is equal to 2 over x plus 3. This is an example of a rational expression. Since it's equal to f of x, then we would call it a function because we have an independent variable and a dependent variable. Since the x is found in the denominator of that fraction, that is what identifies it as a rational function. So, by definition, it's a rational expression in which the independent variable is in its denominator. One of the other key things about your work with rational expressions is stating restrictions on the variables. And so, in fact, when you do state restrictions, they lead to a key feature in the overall function, and that is a term called asymptotes. So you'll see this word come up frequently when we're dealing with rational expressions or rational functions. So asymptotes are basically restrictions on the variables, which lead to regions, or in this case lines, where the function does not exist. So if we could identify the restrictions on a function, then we can address this feature called asymptotes. So going forward, we're going to try a couple of examples of graphing, and then we'll be given the graph of two different rational functions and we'll determine their equations. So in example 1, we have f of x is equal to 6 over x minus 3 subtract 4. So the restrictions on the variables, let's take a look at the denominator of this fraction. What we know about denominators is that they cannot equal 0. So if we take this portion out of that fraction and say that x minus 3 is not equal to 0, then when we solve this inequation, x will not equal to 3. Well, this leads to what's called the domain of that function. So we would say domain equals to, and we have those braces, x belongs to the real number system, so xer, such that x is not equal to 3. And so what this then represents is a line that's in the graph where the function does not exist, and we'll address that once we get to the sketching part. Now for the range has to do with the value that's at the end of the equation, this value here, subtract 4, and that is the restriction on y. So we would say, in this case, the range, once again with braces, we would have yer, so y belongs to the real number system, such that y is not equal to negative 4. And once again, this represents a restriction on the y's, and so we would go to that location in the coordinate system to determine where the function does not exist. So we're going to proceed to that particular position in the coordinate system, and then we'll plot a point. So at 3, negative 4, we plot a point which represents the location where asymptotes will exist. So we're going to draw in some lines that pass horizontally and vertically through this point. And what I recommend is that we use dashed lines just to represent asymptotes. So there we go, we've got the asymptotes in place. And now what we need to do is sketch the actual curves that form our function. Now if we go back to the equation, the one number that we haven't used yet is the 6. And this value that's found in the numerator of our fraction is going to be key to helping us determine points that belong to our curve. So we're going to take that value out of the equation, 6. And what we're going to do with that is we're going to find numbers that multiply to 6, a pair of factors, and so one pair of factors is 1 times 6. Another pair of factors is 2 times 3. Now we could have reordered them and said 6 times 1 and 3 times 2. That's also possible. And then we also need to address the opposites. So negative 1 times negative 6 and negative 2 times negative 3. And once again, we could have rewritten them as -6 times -1 and -3 times -2. Now, how do we use these values or these pairs of factors to find points that belong to our function? Well, think of this first pair of factors, 1 times 6, as a pair of coordinates. So in other words, 1 times 6 can be thought of as 1 comma 6, but not relative to the original origin, rather relative from the new origin. That is where the asymptotes meet. So if I go from this point, I will then go to the right 1, which is +1, and then up 6, and plot a point. And this point belongs to the rational function. Then I could have had the opposite, that is 6 times 1. So going back to the new origin, I would go to the right 6 and up 1 and plot a point. And that point belongs to the function. 2 times 3 would become 2, 3. So from here I go to the right 2 and up 3. Plot a point, go back to the new origin, to the right 3, up 2. And there we have sufficient number of points in order to connect the dots to form our first branch of our function. Then the second branch of the function will come as a result of these values, and so from the new origin to the left 1, that's -1, and down 6, plot a point. Continue to draw the other points to form your second branch. And so that completes the two branches of the function 6 over x minus 3 minus 4. In our next example, the equation is written in backwards order here. So we're going to put the fraction first. We're going to rewrite this so that the fraction is first and then the 6 is at the end. Now, to state the restrictions on the domain, notice that in the denominator of that fraction, it's an x plus 2. If it's going to equal 0, which it cannot, but if it was to, then the restriction would be that x cannot equal -2. And as far as the range is concerned, it's that number that's at the end of the equation. And so now this location at -2, 6 represents the location of the horizontal and vertical asymptotes. And now use the given value that's in the numerator of that fraction, which is -3. We're going to write pairs of factors that multiply to that value. So we will have 1 times -3 as one option, or we can have -1 times 3. And we, of course, can reverse the order of those two numbers. In fact, we could even go to decimals, and we can say, well, what if we went to 0.5? 0.5 times what gives us -3? The answer would be -6. And of course, we can attach the negative to the 0.5, so we would have -0.5 times 6. And so now we're ready to use these pairs of factors as coordinates to plot relative to the new origin. So from the new origin, we can use the first pair of factors, which are 1 times -3. So from the new origin, 1 to the right and down 3. Okay, as another option, we could go to the right 3 and down 1. Remember that if we go to the right, that means a positive value, and so therefore we would have to go down to get a negative value, so that the product would be a -3. And if we were to use the 0.5 and the -6, we would go to the right 0.5 and down 6. And we can also go to the right 6 and down 0.5. So there we get the two branches of that function. Now, to determine the equation of a rational function, we'll start by drawing in the asymptotes for the function. Looks like those are the best locations for them, so that when you look at the curve, it looks like it fits in nice and symmetrically. So the next step is to determine the equation of those asymptotes. It appears that the horizontal asymptote is at y equal to -1. So that will translate into a part of our equation. And for the vertical asymptote, it looks like it's at x equal to 2. So we can start off by saying f of x is equal to, and put our restrictions into the equation. So for the denominator, we'll have an x minus 2, so that when we plug 2 into the equation, we'll see we get that 0 in the denominator. And then -1 at the end of the equation, which represents the horizontal asymptote. Finally, we need to figure out what number will go into the numerator. If I pick a point that's easy to read from the graph, like this point right here, then how do we get from the new origin to that location? We would have to go to the right 4 and up 2. Both are positive directions, 4 times 2. And so that tells us that the numerator of this fraction will be a positive 8. And so that leads to the equation of that function. Of course, we could have chosen a different point on that curve. We could have chosen this point that's up here, and to get to this point we would go to the right 1 and up 8. And so 1 times 8 will give us that 8. So it doesn't really matter which point you choose, just make it convenient for yourself, and you multiply those two values together to find out the numerator of that fraction. Looking now at our final example, we draw in our asymptote. For the vertical asymptote, we have x is equal to -4, and for the horizontal asymptote, it looks like it's y equal to 3. So then we'll write the equation f of x is equal to, write our fraction, into its denominator we'll have an x minus 4 in order to, x plus 4 in order to accommodate that restriction of -4, and a plus 3 at the end of the equation to accommodate that horizontal asymptote, the restriction on y. Now to get the value that goes into the numerator then, once again we pick a point that's on the curve that's easy to read the coordinates, such as this point right here. To get to that point from the new origin, we need to go to the right 4 and down 1. So the product of 4 and -1 is -4, so our numerator of the fraction will be a -4. So if you found this lesson to be useful and you like this style of teaching, then please subscribe to my videos, check out more of the videos, and if you think that your friends might benefit from this lesson as well, then please share it with them too. Thank you, and bye for now.